Hello everyone, my name is Anton Lukashchuk. I'm coming from EPFL Lausanne, group of Tobias Kippenberg, and today I'm going to deliver you a talk, Microresonator dual comp coherent FMCW LiDAR. So this is the outline of my presentation. We'll start with a brief introduction to LiDAR and FMCW LiDAR in particular. Then we'll jump to Microresonator Soliton-based FMCW LiDAR. Then we'll talk about dual comp spectroscopy and multiheterodyne technique. And finally, we'll go to dual comp FMCW LiDAR. So to begin with, LiDAR stands for light-based detection and ranging. And for any LiDAR, you need a laser which illuminates the target, and then you need a detector when you collect a reflected beam. So the most popular implementation of LiDAR is time-of-flight LiDAR, where effectively you measure the time between the moment when you emit the pulse and the moment when you receive it, and then you transfer this time to the distance with this simple formula. The pros of the time-of-flight LiDAR are ease of manufacturing, it's relatively cheap, and they are current market leaders like Velodyne and Oster. As for the cons, they have limited range and resolution, which is determined by the width of the pulse. For example, for 100 picosecond pulse, you get only 3 centimeters. And they also suffer from the crosstalk and interference from other sources, and they do not have access to direct velocity measurements. To kind of improve your LiDAR time-of-flight LiDAR system, you parallelize it, you introduce multiple sources, but however, you suffer from crosstalk and you need to mitigate that one. So you implement sequential switching or spatial filtering or time-gated detection. And that means that effectively each of the lasers operates in its distinct time window. Or you can use a flash LiDAR systems, which however requires high energy pulses and again suffers from the crosstalk. If you imagine you have a flash LiDAR car next to you and it will illuminate you. So another implementation is frequency modulated continuous wave LiDAR. And the idea here is that you send a chirped pulse to the target, and then you collect again the chirped pulse. And here's the principle of the operation. So the dashed line stands for the signal, reflected signal, and the solid line stands for the reference LO. So it's not shown here, but what's really important is that you perform a heterodyne detection, where on the detector you combine the reflected beam, and at the same time you send a reference, which would be a local oscillator as well from the emitter. So here you have a signal and reference, and you can see here that the time information is encoded in this shift, relative shift, while the velocity information would be encoded in this vertical shift, which comes from the fact that if your target is moving, a reflected beam would have a Doppler shift. And performing simple algebra, you can retrieve a distance and radial velocity of the target. And of course, those parameters like frequency excursion, what's the amplitude of your chirp, as well as how fast do you sweep the chirp. So the period would be kind of some parameters which would determine the performance of your LiDAR. And as for the pros of the FMCW LiDAR, you have higher receiver sensitivity, meaning increased range. You have minimized interference, and you do not suffer from ambient light. Then you have direct velocity measurement. But as for the cons, you need a really good laser. It must be a narrow line width, and you need to have a good control over the chirp linearity. And then you need to perform some of the digital signal processing. Just to give you a bit of the flavor, I put some numbers here. So for example, for the work that we did, the frequency excursion B is 2 gigahertz in our case. So how wide we sweep our chirp, then how fast we do it, it's 10 microseconds or 100 kilohertz speed of the sweep. And the carrier, in our case, the wavelength is 1553 nanometers. And if you imagine that you have a static target 200 meters away, that means that your bit node would be at around 260 megahertz in frequency. So the frequency that you would detect would be around 260 megahertz, and your trapezoids would be at the same height because you wouldn't have a velocity, and the velocity comes from the fact that you would have a split here. And if you right now imagine that you have a velocity, a target 200 meters away is moving at you at 75 kilometers, or from you at 75 kilometers per hour, then you would have a split between those trapezoidals, between f up and f down, and the split would be around 30 megahertz. So this is just some numbers, and you need to remember that we have an ambiguity range, which comes from the fact that if you move the signal over one period, then effectively this picture doesn't change. So that means that if you multiply this time period by c, you get 3 kilometers, and this is your ambiguity range, so that you can measure your distance from 0 meters to 3 kilometers. And distance resolution is this formula c over 2b. So once you increase your frequency excursion, once you sweep your chip wider, then you can have resolution. And for 2 gigahertz frequency excursion, you have 7 centimeters resolution, which is really good for LiDAR. So if we want to improve our FMCW LiDAR, we want to parallelize it, then we need again to introduce multiple sources. And the problem here is that it's already not that easy to obtain a narrow line with a laser which has a really good chirp control. And if we somehow try to multiplex already existing source, then that wouldn't work, because we would again suffer from the crosstalk, as that they would operate at the same frequency, and that would be a problem. It appears not to be easy. And here we want to here we again ask ourselves the question. Again, imagine we obtain that narrow line with source with well-controlled chirp. Is it somehow possible to demultiplex it, and to demultiplex it in the way that it goes through different frequencies, so that we will not suffer from the crosstalk, because different frequencies are kind of orthogonal, and then we can use those distinct sources as distinct LiDAR sources and perform the measurement for every distinct source. And apparently it's possible, and this is what we have recently done with my colleagues at EPFL. And the platform that we utilize is a Microresonator. And before I explain to you how it works, so let me briefly dive into the frequency comp subject. So to obtain a frequency comp, what you need a strong enough continuous wave pump, high quality microresonator with a kernel linearity. And due to this kernel linearity mediated interaction of light and media, you can have 4-wave mixing. This parametric process, degenerate or non-degenerate 4-wave mixing, which will give birth to these sidebands. And the cascaded 4-wave mixing results into the frequency comp like that, where you have an equidistant spacing between the optical sidebands, which is determined by the free spectral range of the microresonator. And to tune into the frequency comp state, to generate frequency comp, what you usually do is that you tune your pump from the blue detune side towards the resonance, towards the red detune side. So you tune your pump like this. And once you tune into the pump, first of all, you start, so this blue trace corresponds to the generated light into the cavity due to the 4-wave mixing. So if you filter out the pump and you look at the power that you have in another frequencies and another sidebands. So once you tune into the resonance, you start to observe 4-wave mixing, and you generate a so-called noisy comp. And this is the spectral picture of the noisy comp, and the time domain corresponds to the chaotic waveform. But it was found in 2013 by Tobias Kerr that once you're effectively redetuned, from the cavity, your time domain self-organizes into the solitons, which kind of spectral picture looks like that. And those solitons, they're nice structures because they are fully coherent, in essence that you have a fixed phase relationship between each of the optical lines. So, and of course, they correspond to the solitons in the mode-locked lasers. And we have obtained those solitons from tens to thousands of gigahertz. They can be as short as 50 femtoseconds. They are low noise. They can be broadband, and they have low line-to-line power variation and determined by the second's hyperbolic profile. And if you zoom in, then you can see that you have a fixed relationship for the optical frequencies of the comb lines. which can be parameterized with these two values: repetition rate and FCO or F0, which corresponds to the global offset of the frequency. And so in time domain, you said it corresponds to the optical train of pulses. So those solitons can be described through the Lugatti-Lefevre equation, which is kind of equation, double balance equation. On the one side, you have a balance between dispersion and linearity, and on the other side, you have a balance. You need to have a balance between loss and gain. And the fundamental solutions of this Lugatti-Lefevre equation, so the propagation of the light in the microresonator, the solution is the trivial one, continuous wave background, and there is also Soliton solution. And to distinguish this Soliton solution from the conventional Soliton solution in nonlinear Schrödinger equation, we call those Solitons dissipative Kerr Solitons. And just to briefly mention, the platform that we work on is silicon nitride. So silicon nitride is a nice material because it's fully CMOS compatible, and it also features a high chi3 nonlinear coefficient. Furthermore, once you assemble a microresonator, integrated microresonator via this silicon nitride material, so that means that it guides the light. Those microresonators have extremely low losses, and this was enabled by the Photonic Damascene reflow process, which was developed at EPFL. And I will not go through the details, but I just briefly mentioned that the main difference here is that you do not etch the silicon nitride itself. First of all, you perform etching of the silica, then you perform reflow, and only then you deposit silicon nitride. And you perform planarization to get rid of the excess of silicon nitride, and then you perform cladding. And this Photonic Damascene process allows us to have extremely high quality factors, more than 20 million, which corresponds to the intrinsic line width of 10 megahertz. And this is the most probable value for the all of the resonances on the batch that were measured. And this is how the chip looks like, 4x4 millimeter chip with here it's 100 gigahertz microresonators, where the radius is around 200 micrometers. And solitons, which we generate in these microresonators, have found enormous amount of applications, starting from astronomical spectrometer calibration, going to ultra-fast ranging, which I'll cover later, multi-terabit coherent communications, optical coherence tomography, integrated atomic clock, frequency synthesis, and dual-cone spectroscopy. Okay, and coming back to our LiDAR story. So imagine that right now we have a chirped source. We have a chirped source, which in time domain looks like that, and in frequency domain it's oscillating sideband. And we use it to pump our microresonator to tune it to the Soliton state. And once we tune to the Soliton state, effectively we have an envelope which looks like that. It's a pulse train, Soliton pulse train, which we usually obtain. But right now what we have is that underlying carrier is still chirped. And if you take the Fourier transform of this thing, then you have the same frequency comb, but where every comb line is oscillating in unison. And why it's possible on the frequency combs? Because once you sweep the pump, effectively means, if you recall this formula for frequency comb, that means that you sweep the FCO while keeping the repetition rate constant. So you keep the repetition rate distance between the lines constant, but if you change the global frequency, that means that you effectively sweeping the whole frequency comb. And this is what we do. Here I want to mention that, so we do it in microresonators, but it was also kind of the same work was also performed with the electro-optical combs. And how it looks like in the lab. So this is our setup. We use the silicon nitride microresonator. We pump it with our laser. We generate the Soliton state. And once we have generated Soliton state, we turn on our function generator. And here we have electro-optical modulator so that we sweep the pump. And once we sweep the pump, then of course, every line of the Soliton is also swept. And then we use some diffractive element to eliminate the scene. and perform a heterodyne measurement. We use a demultiplexer to demultiplex each of the comb lines separately and send it to the photodiode. So we have a distinct amount of kind of single FMCW sources, and we can perform, for each of the comb line, we can perform a FMCW measurement and determine the pixel velocity and distance measurement. And here we have a digital processing array. But here we have a question: how fast this, how fast can we sweep this frequency comb FMCW LiDAR, and how far in terms what's the amplitude can be? And these are the parameters that determine the performance of the FMCW LiDAR. So we should know that. And to answer this question, let's recall again the Lugatti-Lefevre equation. And if we analyze this Lugatti-Lefevre equation and plot the stability chart, then we can see that we can have different solutions for this equation. So this white one, where we have only trivial solution, and here we have some combs. But what very interesting is this green one solution. And again, we have a detuning and we have a power, so the parameters that determine those solutions. And what you can see that for this green region where our soliton exists, we can vary the detuning while still keeping our soliton state alive. And variation of the detuning, that means exactly that at the zero you have your cavity, and here you have your pump. So that means that you can vary your pump, the frequency of your pump, while still having the soliton state. And once you're varying this pump, effectively you perform frequency modulation. This is how you obtain it. And in our experiment, coming, if you want to know the real values, this detuning, the amplitude of the tuning corresponds to 2 gigahertz, and the power, the real power that you need is around 1 watt. 1 watt, the power that you pump into the chip, optical power. But there are also some subtleties. The subtlety is the nonlinear response. So if you look at those two extremes of the detuning, so this is how your frequency combo looks like at those two extremes. And according to the previous works, we know that there is a Raman cell frequency shift, which comes from the interaction of light with the vibrational modes of the media. And this means that even though we don't want it, but we will have a slight change in the repetition rate, because effectively when you have a Raman cell frequency shift, that means that you have a different group velocity. So once you perform a frequency modulation, you jump from this blue state to red one and back and forth, and then you also vary the group velocity back and forth. And if you vary the group velocity, then it means that your pulse would be traveling faster or slower, and that means that you would have a different repetition rate. But we perform the simulation, and we see for the 2 gigahertz amplitude and detuning, our repetition rates only varies for the value of around 10-15 megahertz, and furthermore it varies linearly, which is really good, because that means that you can calibrate for that once you know that it varies linearly, and it's only 1.3% from the detuning, and furthermore it's really a low value. So to kind of study this chirp transduction from the pump to different optical sidebands, we perform this simple experiment where we use a demultiplexer and we select different optical sidebands, and then we beat them with the reference laser, and we analyze the chirp, how well are they chirp, and we can see that the chirp is fairly well for 100 kilohertz, even if we sweep as fast as 10 megahertz. And we can even sweep faster, but we were limited by our electronics. And in principle, theoretically, the cavity limit, the limit should be the cavity limit, because cavity works as a filter, and it should be kappa squared, where kappa is the total line width of the cavity. And we performed a simple mock-up experiment where we analyzed the velocity profile of the flywheel. So this is the result that we obtained. We could get that velocity profile of the flywheel, also measuring the distance at the same time. And then we also performed a simple imaging of this system, where we got out the logo of our university on the first sheet, and then we had the background sheet. Yes, and if you are talking about the advantages of the FMCW LiDAR, we have a simultaneous measurement of distance and velocity, distance at long range. Then it's truly parallel that we have multiple channels. We can attain a high precision as our frequency excursion can go to 2 gigahertz and more. And you can think that as you use frequency comb, then you need to scan only in one dimension. Like here, you need to scan only vertically because horizontally you already have dispersed the frequency comb. So it's another advantage. But then you can think, but okay, can we further improve our system? Can we get rid of the main disadvantage is that we need an N photodiodes, where the N is number of the channels, optical channels that we use, and we need also demultiplexer. And if we want to put the system on the chip, it's not it will occupy some space. Can we somehow improve that system? And yes, we can do that. For example, here we can use a coherent receiver, and this is the coherent receiver on the chip, high bandwidth coherent receiver. Effectively, that means can we get rid of the N photodiodes which perform measurement like this, and can we perform the measurement in a frequency axis? So can we leverage the frequency dimension to get rid of the N? Can we transform our system from physical dimensions where we put some N of the photodiodes, and can we do the measurements, N measurements in the frequency domain? And once we think in these terms, so we directly go to the dual cone spectroscopy, because this principle has already been realized in dual cone spectroscopy. And the kind of the easy intuition comes here. If you look at this picture, how you optically would like to detect this absorption feature. And imagine you have an optical frequency comb with these dashed lines, and you want to read it out, and then you have another frequency comb with the slight repetition offset, and you also send it through this absorption feature. But once you send this optical signal on the electrical photodiode, you can see that you will have a bit nose between each of those closed lines, and you will have the same picture, but in the RF frequency domain. And you can already see that in principle, we can use the same thing for the LiDAR. If our dashed line is the FMCW sources, then we can have an LO comb, which is offset. And we can right now have this N lines, transfer the signal from N lines, transfer to the kind of RF frequency dimension, where they would be separated by the delta repetition rate, delta FRAP, whereas the delta FRAP is the difference in the repetition rates. And to explain this wonderful technique, dual cone spectroscopy, this is the representation in time domain, which means that effectively you need a low train of pulses to sample the signal train of pulses, and the time you need to sample it when the pulses again coincide. Yes, and you can obtain if you sample the signal on the low bandwidth, I want to mention low bandwidth photodiode, you can obtain this interferogram, and once you obtain this interferogram, you take the Fourier transform of that one, and your Fourier transform will give you this absorption feature, which is where the same result can be obtained from this frequency domain point of view. And initially, this technique was developed to overperform the Fourier transform infrared spectrometers, and it has lots of advantages like high speed of acquisition, no moving parts, ease of operation, ultra high resolution, absolute frequency accuracy, and so on. Just to give you a small number of applications in frequency dual cone spectroscopy, it's a linear dual cone spectroscopy, which I have already mentioned. It's non-linear dual cone spectroscopy, where you use a signal comb to excite, let's say, vibrational modes of the media, and then you use the second comb to read them out, and you can obtain those high perspectral images where you detect those vibrational modes of different gases, and you can determine them. Then you can also perform dual comb ranging, where you use a low comb to sample the signal from the target and from the reference, and you can perform ultra fast, ultra precise distance measurements. And then you can also perform a two-way time frequency transfer. And dual comb ranging was also performed in the Microresonator platform, and we could do it extremely. So we performed that work with the collaboration from KIT with Christian Kuz, and we could do it as fast as few microseconds and achieve sub-micrometer precision, so that we were able to read out the profile of the bullet. So it's extremely precise, it's really fast, but the problem here that it has low ambiguity range. In this case, it was 1.6 millimeters, determined by the free spectral range of the train of pulses, 10 gigahertz. So this is the disadvantage of the thing. And what do we do, or how do we do? Coming back to our story with the LiDAR, how we further improve it and have a real LiDAR of long distance measurements. So as said, we have a signal comb, which I showed you before, and then we also generate an LO comb, but which would have a repetition offset T and delta T train of pulses. And again, we do it by generating two solitons from a single laser. And once we have an LO soliton, which we send to a coherent receiver, and then we have a signal comb, single soliton, which would be reflected from the target and also sent to the coherent receiver. And I'll explain to you in the next slides how it operates, the coherent receiver. And so the main idea here is, as I said, just imagine for the channel +1, you would have, once this channel is swept, it goes like this. But when you beat with the LO comb, the signal would be around, and in this case, our delta FREP is 500 megahertz. The signal would be around 500 megahertz baseband frequency. For the second channel, our basement signal, our signal would be centered around 1000 megahertz. And from -1, our signal would be centered around -500 megahertz, or for channel -2, around -1000 megahertz. And for the pump, of course, around 0. But you can ask me how we can distinguish positive frequencies from negative, and it's really easy once you do coherent detection, so where you have an optical hybrid and two balanced photodiodes, so that you can obtain two quadratures of the RF signal I and Q. And once you obtain two quadratures, you can infer the full spectrum with the positive and negative frequencies. And this is how it looks like, really. So you have signal comb, and then you have a LO comb. And then signal comb is reflected back, and it obtains a shift, vertical shift and horizontal shift for the distance and for the velocity. And you can send it to the one coherent receiver. And you can see that every channel would be spectrally separated, because every channel would occupy only its window. And as I showed you some values at the very beginning, you remember that, for example, the distance of 200 meters would slightly correspond to the 200 megahertz. So meaning that even if we want to measure 1 kilometer distances, it wouldn't go really far. And here we have the separation of 500 megahertz. So the separation between those channels is enough to perform measurements. And here our formulas are slightly modified for distance and the velocity, because right now we introduce the notion of negative frequencies. That's why the formula becomes slightly modified. And for the velocity, what we should remember that we need to estimate the global shift of this trapezoidal from the baseband frequency. And that's why this formula would be like that, slightly modified as well. And this is our measurement. So these are two our comb, signal comb and a LO comb. And once I send this thing to the coherent receiver, I can obtain this interferogram recorded over one period. So this is the Fourier transform of the signal over one period, where I can determine again positive and negative frequencies. And if I do short-time Fourier transform, so that you can see what are the frequencies for, let's say, this one period of 10 microseconds, or two periods for 200 microseconds, you see that I have those F up and F down, but my signal is corrupted with some noise and also some images. And those images come from the fact that my IQ coherent receiver is not really orthogonal, so that my I and Q components are not really orthogonal. So there is some angle of rotation between them, but we can compensate for that image if we know the prior information that this, for example, image here comes from this signal here. So we are able to do some post-processing, digital signal processing, and compensate for that, and obtain those clear traces from which we can calculate F up minus F down or F up plus F down and determine signal velocity. And we can do it for multiple channels, as you can see, but somewhere still we have too much noise and we are not able to detect it. So, I mean, it happens. that we cannot determine the signal here, or here we also had some problem with the image and signal. And then we determined, then we performed again a mock-up measurement. We determined the velocity profile of this rotating wheel, flywheel, simple toy car motor. And again, we were able to measure those velocities. And so on field circles correspond for 1 period measurement time, and field circles correspond for 10 periods measurement time, so that we, because for some measurements, as I have already said, the signal couldn't be measured because due to the lack of SNR, because we have some limited amplification bandwidth of our amplifier. And at Crown et al., we have demonstrated FMCW dual comp LiDAR. It is massively parallel, and it performs massively parallel sampling. It determines velocity and distance simultaneously. It can be detected on a coherent receiver. It can be integrated on a silicon chip. It has high distance resolution. It can go up to 100 kilohertz and more. And if you consider 25 channels, you will obtain 2.5 megasample speed. And furthermore, you can improve that system if you introduce semiconductor optical amplifiers to have a high amplification bandwidth. So this brings me to the introduction. Thanks for your attention. I would like to thank my group and all of the acknowledge all of my colleagues contributed to the project. And also silicon nitride chips can be bought at Lighting Tech company. Thanks for your attention.